So let's start with the webinar RESTrade Rest. Hello everyone. Welcome to the second session of this series of webinars. It started last week with the presentation of Backbone and Emiris, and today we will have two more presentations. My name is Fernando Lezama, and I will be the host of this session. Just to give a little bit of context before starting. The webinar is on the scope of RESTrade Rest project, which is a European project, H 2020. It has different partners from different parts of the world. And this project is the main target is to develop tools for the design and modeling of new markets and negotiation mechanisms for a 100% renewable European power system. The project started in February the 1st, 2020, and it will have a duration of 48 months. So in this webinar, we will have two presentations. The first one will be related to MASCEM, and it will be given by my colleague and friend Gabriel Santos from ISEP, GECAD. MASCEM is a multi-agent simulator platform for competitive electricity markets. It's a modeling and simulation tool designed to study complex restructured electricity market operations. And Gabriel Santos, well, something about him, he received his bachelor degree and master degree in informatic engineering from the School of Engineering of the Polytechnic Institute of Porto in Portugal. And also he holds a Ph.D. degree from the University of Salamanca, Spain. His research interests include multi-agent systems, ontologies, electricity markets, decision support systems, and smart grids. He will give the first presentation, and after that, Hugo Algarvio will present RESTrade. RESTrade is also a multi-agent trading platform of renewable energy sources, which includes different models that also encompass traditional power and energy balanced markets, and also upgraded version of them. Hugo Algarvio is a contracted researcher at LNEG, and he has a bachelor degree and master degree in electrical and computer engineering and a Ph.D. in sustainable energy systems. His main research interests are related to the use of multi-agent technology to model and simulate present and future electricity markets and the market agents' behavior. So the presentation will have a duration of around 30 minutes each. I ask to the audience that they can make questions in the chat, and also they can make questions at the end of each presentation. So if you want to make direct questions, we will have a small session of questions and answers at the end of each presentation. So without further ado, I leave the floor to Gabriel Santos with the first presentation. Thank you very much, everyone, to come to this session.
Thank you very much, Fernando. I will now share my screen. Can you see my screen?
Yes.
Yes?
Yeah.
Thank you. So, good afternoon. Welcome to our webinar about MASCEM, the multi-agent simulator of competitive electricity markets. My name is Gabriel Santos, and I kindly ask you to keep your questions to the end of the presentation. You can, like Fernando said, leave your questions in the chat, or if you prefer to do them live, you can use the raise hand function at the end. So I will start with MASCEM's overview. Next, I will explain the integration of MASCEM's agent-based model into the SPINE toolbox, which is a toolbox used within the scope of RESTrade Rest project. Next, we'll take a look at MASCEM input and output models for different market types and different mechanisms. We will also see how to run it. And finally, I will present a live demonstration of a case study using MASCEM within the SPINE toolbox. So, MASCEM is a simulation and modeling tool which has been developed for the study and simulation of electricity markets operation. MASCEM models the main market entities and their interactions. These entities are implemented as software agents, and examples of such are the market and system operators, the buyer and seller agents, and also aggregators. The market operator is the agent responsible for regulating pool negotiations by validating and analyzing the players' bids, depending on the type of negotiation they are dealing with. And this agent is also responsible to determine the market clearing, namely the market price, the accepted and refused bids, and the economical dispatch to be sent to the system operator. The system operator, in turn, is the agent responsible for examining the technical feasibility from the power system's point of view. This agent tries to solve congestion problems that may arise to ensure the system's security and that all conditions are met. Buyer and seller agents are the key elements of electricity markets. So a buyer agent can be a consumer, a big consumer, like an industry or a commercial building, or even a distribution company that is allowed to participate in wholesale market to buy electricity. On the other hand, a seller agent may be an electricity producer or any other entity allowed to sell electricity in the market. And the aggregators, in turn, are special types of players who gather consumption and generation from small players to enable the participation of these small players in the wholesale markets. And this way, these players can compete with the big players in the wholesale. MASCEM includes day-ahead, intraday, bilateral contract, and forward markets. For each scenario, the user must input which market to simulate and respective market type, the number of simulation days, the number of participating players, and their strategies if desired. MASCEM accommodates the simulation models of 3 of the main European electricity markets. These are the Iberian electricity market, MIBEL, the European Power Exchange, IPEX, and the Northern Europe electricity market, Nord Pool. MIBEL, which is composed by Portugal and Spain, is a double-sided auction-based electricity market for the trading of electricity for the next day. Bids for each period are composed up to 25 tranches of energy amount and price per megawatt hour. And in the day ahead, market sellers can include complex conditions to constrain their bids. These conditions, if not respected, these players are not interested in participating in the market and thus are removed from the respective pool. On the other hand, the intraday market is complementary to the day ahead and tries to adjust the outcomes of the day ahead market. This means that only players that participated in the day ahead market are able to participate in the respective periods of the intraday market. This also means that buyers can sell in this market, in this intraday market, and sellers can buy, and both types of players can submit complex conditions to constrain their bids. In MASCEM, both market types are included. IPEX, like MIBEL, is also a double auction-based market for the power exchange for the next day's 24-hourly periods. Bids in this case can be composed of up to 256 combinations of energy amount and price per megawatt hour. And instead of complex conditions, the IPEX spot includes block offers. These offers connect multiple periods, and they are either accepted for all the block periods or they are rejected altogether. So this can be seen as a type of indivisibility constraint. In MASCEM, only the day-ahead type of IPEX is implemented. Finally, the Nord Pool market is very similar to IPEX, as it also includes block orders instead of complex conditions. It also runs for the 24 hours of the next day, and the bid in this case can be composed up to 64 pairs of energy amount and price per unit. Additionally, it also accepts what is called the flexible orders. This type of orders allow to make additional sale offers, only for sale, and are transacted in the period that maximizes the overall social welfare. This means that these bids are not submitted to a specific period, they are just placed, and then the market operator uses an optimization algorithm to verify where these bids can be settled. In MASCEM, also, like at PEX, only the day-ahead market of Nord Pool is available. Besides the 3 European electricity markets, MASCEM also allows the simulation of the double auction and single-sided auction market models, namely the symmetrical and asymmetrical pools that we see in the images, and these are the most common trading designs for electricity markets. In the symmetric pool, as we can see here, the seller's bids are ordered from the lowest price to the highest price, while the buyer bids in the other way around, from the highest price to the lowest. In the point these both curves intercept, not only is determined the accepted demand, but also the market price, which is defined by the last seller to sell. On the other hand, taking a look at the asymmetric pool, we can see that the buyers only submit their demand, the required demand, while sellers continue to submit a pair of supply and price per unit. As you can see here, they are ordered in the same way. The total demand defines the accepted demand in the pool, and the market price once again is set by the last seller to sell. In the scope of the TradeRes project, MASCEM models were integrated in the Spine Toolbox to ease their integration, the integration of these models with models from different partners. If you want more details about Spine Toolbox, please feel free to follow one of these QR codes or URLs to learn more about it. So, to make these models available within the Spine Toolbox, we have extracted the market and system operators models from MASCEM and made them publicly available as web services, facilitating this way its access and reuse within the Spine Toolbox. Again, if you want to learn more about these services, please take a look at our services web pages. So, the MASCEM models made available for the TradeRes project include the MIBEL, IPEX, and Nord Pool electricity markets, as well as the symmetric and asymmetric models for the simulation of a single period. In any case, the inputs are passed using the Json notation. In this table, we can see snippets of input examples for MIBEL, IPEX, and Nord Pool respectively, and I would like to start to highlight here the property market type, which is only available for MIBEL, since in this case is only the day-ahead type is implemented. And in the case of MIBEL, the user can select between day-ahead or intraday. Also, I would like to highlight in the bottom the constraints that can be submitted to each of these markets. Here you can see complex conditions, block offers or block orders, as well as the flexible orders. In any case, it should be noted that these are optional, so the user is not mandatory for the user to submit at every simulation this type of constraints or bids. So they can be used only if required. Something I would like to highlight too is that the energy and price units must be normalized by the user. Okay, so they represent the same unit for all bids. Here we have input examples for the symmetrical and asymmetrical models respectively, and I would like to highlight the difference between the asymmetric pool on the left, where the demand bids from buyers do not include the price, only energy, and in this case for the symmetrical pool we already see the energy and price pair. For the supply it is the same. After the market execution, there's the power flow validation from our system operator. And this table here, we can see a snippet of the input of this power flow model. We can see here in the start the name of an existing network in our services database. Okay, and here are some elements that we are updating from the base network for buses, lines, and also from the connection to external grids. So the user is able in this input or to submit a completely new network. If it does not exist, our system will keep it in the database. If it already exists, then it will update these parameters accordingly. So we have a different scenario. Here in the bottom, you can see also the power flow algorithm we want to run in this specific example and the result type. Given that we are simulating in the Spine toolbox and for manipulation of data, we prefer here to use Json, but the Excel files are also available from our service. In this case, we have an example of the player buses mapping file, which makes the mapping between the players that are part of our electricity market and the bus in the network where this player load or generator is connected. Regarding the outputs, here we have two different types of outputs, and these depend on what we are simulating. For electricity markets, it will be something similar to what we see here on the left column, when we are simulating the symmetrical and asymmetrical pools, then the result will be something similar to this. In this case, we can see here, we are seeing the results for Nibel. From the session property on, we have to the bottom, we have the session results. Here we can see some aggregated data from the complete session. Okay, these are sums from different values for each period. Here we can see the player results list, and for each player has his own player periods results, where we see the results for the first period, for the second, and in the second period we can see that this player has been removed because of one of these complex conditions. In the bottom here, I would like also to highlight that in the perspective of the market operator, we have also the aggregated results or the sum of different metrics for each period. Regarding the period pool output, we can see here that for this period, there was trading. Here we have the trading results for each bid submitted or for each tranche of the bid, and here we have some aggregated metrics also. Finally, taking a look at the output example of the power flow, we can see here the power flow results for different elements of the network with different metrics. Here for the buses, for the lines, the loads, the external grids, and using, for instance, this value from buses, we can validate if the tension in the buses is within limits or not. The same for the lines, we can verify using these results if the lines are having any congestion, or also for the transformers and so on. So here we have the publicly available example that we have prepared in the Spine toolbox. And this example provides the base for simulating MASCEM electricity market and power flow models, not only within the scope of TradeRes, but also for any interested party or stakeholder that might find it interesting to use this tool. In this specific example, we will be executing Mibel day-ahead market, and we are validating the power flow of the power network constraints according to these market results. So, as we can see in the picture, we have 5 different components inside the MASCEM demo Spine toolbox project, and starting with the first component, the input Mibel. It is the input of the Run EMS tool, okay, and contains information regarding the players and their bids for each period. Here we can see there's a public schema available to validate this input, and here we have also an example of input file that can be reused and edited, so any stakeholder or any other interested party can execute this project. It is important that the input file of this tool for this component is placed in the Run EMS folder. Regarding the Run EMS tool, it will be executing Mibel day-ahead market and validates the input against the respective schema of our service. Here you can find an output example in the Run EMS folder /output folder, okay? But we'll be taking a look at this at one of these examples later in our session. The results of the Run EMS tool are then sent as input for our Run PFS tool, which will be simulating our system operator. The input PFS, in turn, is the main input of the Run PFS tool, as it contains the network elements, as we've seen before, as well as the powerful flow algorithm we want to execute and the respective parameters. There's also a publicly available schema that validates this input before being used by the tool. There's also an input file that anyone can use to edit or to use as is to test this example. Again, the input must be placed in the Run PFS folder, in the respective folder. To conclude the inputs, we have the player buses, which is another input for the Run PFS component, and this is the one that maps our market players with the respective network buses. Okay, so there's also a publicly available schema and an example that can be used. Once again, the input file must be placed in the Run PFS folder. Finally, the Run PFS tool, which executes the power flow service, runs our power flow for each period of the market and saves the results locally, as we'll see after. Here, there's also a publicly available schema of our service to validate the input of the service, because here we have to manipulate the base input and with the results of the market to generate the final input. And here you have in our project also a publicly available output example, so you can analyze and verify which metrics and data is being made available. So after execution, as I said, output files are saved in dynamically generated folders named with datetime formats, as we can see in these examples, which allow us to have results for different scenarios or different simulations, keeping them without overlapping with the previous ones. For our live demonstration, we have used the base MASCEM Spine project that I have just presented. The idea was to put ourselves in the shoes of one of the interested stakeholders and prepare a scenario based on real data. For our DEM scenario, we'll be considering the Mibel day-ahead market, and we only consider 8 players, namely 5 buyer agents and 3 sellers. Regarding the network for the power flow validation, we are using the SIGRE high voltage transmission network, which includes 13 buses, 9 lines, 5 loads, 1 per buyer, 3 generators for each of our sellers, 3 shunts, 6 transformers, and it is connected. It has 1 connection to the external grid. And finally, if you want more information about this grid, you can find them using the following QR code or URL. To make our live demonstration more interesting, we have also added a new tool, a chart generator, so we can visualize the results graphically at the end of the simulation. So I will now pass to the running of our demo. I believe you can now see the Spine Toolbox tool. To see how easy it is, I'll be loading our demo. I believe everyone can see. So, yes, thank you. Here we have the inputs. Just to show briefly, this is the link to our folder input file. Here we have the same for the grid that we are defining, the network that we'll be using, and here the mappings between the players and the respective buses. This is our market operator tool. If I double click, you can see here the code that will be connecting to our web service. The same for the power flow. Here we have the link to web service and the code to validate, manipulate in this case the input, validate against the schema and run the service. And here you have also a tool for the chart generator. Without further ado, let's run our simulation. As you'll be able to see, the market was very fast to run. It takes longer to generate the charts for each player, which are not much players. I can start by showing the results of the electricity market in Json, just to visualize what I have explained before. So we have here the session results with different metrics that are basically sums of the different periods. Here we have the same metrics and the sum for the respective period. But if you want to take a closer look to our player results, for each player, it has the metrics, the sum of these metrics for the complete session, and then we have the session results for each period. So, but to make it more interesting, let's take a look at our charts. Not this, I'm sorry, results directory. Here, as we can see, we have charts for different meanings. We have here a session chart, as I will show. Just a moment, please. Okay, I will start with the session chart. Here we can see in the perspective of those metrics of the session in the perspective of the market operator. So we have the total supply satisfied and unsatisfied, and the same for the demand, as well as the market price for each period. Maybe it's not very perceptible, but I will show. We can see here that there were some unsatisfied demand in these periods, but there's also some unsatisfied supply. It's not very perceptible, but in these periods too, and here, okay? So taking a closer look to our players, we have here a buyer who satisfied all this demand, probably because, not probably, mainly because he submitted the highest price. Here we have the seller with the lowest price, meaning that he was also able to trade all the available supply. In this case, we have the buyer with the second highest price, I believe. He's also able to trade everything. Here we can see this one of the sellers that defined the market price for the first 8 periods as well as for the first last. And in this case, we have the other seller who set market price from the period 9 till period 20. And this is also in these periods where the seller is not able to trade all the available supply. I'm almost concluding. Here we have the last buyer. I would like to highlight that although this buyer presents a price higher than the market price, given that there was no more available supply in these periods, he was not able to trade. And here we have, I believe, the last 2 buyers who are able to trade all of the required demand. So to conclude, let's just take a brief look at the results of our power flow. Again, not this, it's here. In this case, we'll be looking only at the JSON file. Here we have the results for the 24-hourly periods. And for each period, you can see the results for the complete grid inside this, but I will start to show you that the power flow returns a valid result. As you can see here, we have the buses, different metrics for the buses, and here each bus of the network, the same for the lines. I would like to show here the loads. These values are the values that were traded in the electricity market and are the values that we are validating. In this case, we have in the loads the buyers, and in the generators, we have the sellers. So, passing to our presentation again. To conclude, here we have some publications where you can find out more details about MASCEM. These publications are also available from our web services website. If you find it interesting, I'd like to learn more about it. And with this, I conclude my presentation. Thank you very much for your attention, and I am now available for any doubts or questions that you might have.
Thank you, Gabriel, for the interesting presentation. There is one question in the chat, and then we can ask to the audience. Tobias Corte is asking, how is the initial model state generated with respect to agents' properties?
Let me read because I'm not sure I'm understanding the question.
It's in the chat.
Yes. How is the initial model state generated? Basically, it's generated by the user, the input. I don't know if this answers the question, but we decide in the input, we configure exactly how the agents start their state, how the agent state starts in the simulation. It's completely configurable. Does this answer your question, Tobias?
Yeah, and what would happen if there is some inconsistency between the agent properties and the model state? This would throw an error or something like that?
Well, honestly, I try to make sure there are no inconsistencies. If they are, it depends on the error itself. There are errors that can crash the simulation, yes, there are, but most cases these are verified before the simulation start and the user is warned about these errors, that something is wrong before the simulation start. But let me just highlight something that probably was not very clear in my presentation. To make MASCEM available within the Spine Toolbox, we use the models that are inside the agents. So the Spine Toolbox is not using agents, okay? It's using the same models that we made available through web services.
Okay, Tobias Corte still makes a comment. So agents are not set up based on empirical data. Okay, he said that he got it now. So maybe we can pass to a second question.
Basically, just to conclude about data, you can use real or simulated data. It depends on what we want to study. If you want to study and compare with a real market, it's good to use empirical data and also data from, if possible, from existing markets, from data that is made publicly available. On the other hand, if you want to test or simulate something that is not happening in today's market, in nowadays markets, then we'll be using data that we generate to see how it behaves in those cases.
Okay, another question. Is this tool MASCEM available through a web service? This was asked by Brigida Teixeira.
Sorry?
If the MASCEM is available through a web service.
Yes, as I showed you, let me show you the correct slide. Just a moment, it's here. I believe you can see these web services are not MASCEM. The first one is for the market operator models that we made available in the scope of TradeRes. It has not all the models that MASCEM accommodates, because when we are dealing, for instance, with bilateral contracting, it's not very interesting to have a web service to simulate this, because the agents bargain with each other to do a negotiation and settle a negotiation if they agree with each other. But in this case, we have only the three electricity markets that I was presenting. And then we have here in the bottom, the model from our system operator, from MASCEM. We do not have here models for players, okay? Because these are inputs that we provide to these services, okay? So the strategic behavior of agents is out of the scope of the models made available in these web services.
Okay, yeah, just one last question that I think that maybe is related to what you just said, from Katia Silva. What kind of criteria can be applied to understand that a certain player should be removed from the session?
Well, that's not a criteria. Basically, we apply the rules from MIBEL, which are publicly available. Let me show you the slide. If you use this QR code, you have there the complex conditions defined by MIBEL, and we use them. If a player submits this complex condition, he's stating clearly that if that rule triggers, he wants to be removed from the pool. And the market operator only respects that decision. It's not the market operator who decides to remove this player, okay? This is a player's decision. So if the player, for instance, the example I showed, the indivisibility, the complex condition, The player only wants to trade if he sells all the amount in that period. If he does not, he doesn't want to trade because probably he has somewhere else where he can trade it for a higher price or a lower if he's buying in this case. No, but in the day ahead they are selling, so he's selling for a higher price. So complex conditions are the decision of the player to use them or not, and they can be used as strategies for these players, okay? So players can sometimes use this as a strategy. For instance, other well-known strategies they can use is to ensure they buy or sell an amount of in the day ahead at a very low price and then sell it if they are a seller, they try to sell at the highest price possible and then try to buy in the intraday at the lowest price. So there are these type of strategies, the buyers the other way around. But regarding these web services specifically, that strategy is out of their scope. So it's not the market operator who determines if a complex condition is going to be triggered. It's the results of the market itself.
Okay. Okay. Thank you. Thank you, Gabriel, for the explanation and
thank you very much.
Thank you for the presentation. So now let's pass to the talk of Hugo Algarvio. Okay, the floor is yours, Hugo.
Thank you, Fernando. Can you see my screen?
Yes. Yes.
Yes. Thank you, and good afternoon, everyone. So I'm going to present the agent-based system RESTrade, which focuses on the balancing market models. So first, I'm going to do a brief overview of the agent-based models provided in the project and the scope of RESTrade in this workflow. Then an overview about European balancing markets and the options of choice that we give to the users about these market elements. Also, the market elements that we are choosing and changing the market design for power systems near 100% renewables. In the end, we will show how we can set up the simulation in RESTrade, how we can install it and run it. And then in the end, we'll do a demonstration on Spine Toolbox. So first, a brief overview about our agent-based models provided in the project. In the long term, you can use EMLab. That is an agent-based system that can provide the participation of agents in capacity markets or mechanisms and the prices of these on CO2 markets, and also the new investments in new capacity. Investments in new capacity can also be done using the optimization models that we have, Backbone and Competes. In this case, using EMLab, agents are deciding which investments they are made. That's not an optimal one. For the markets, you can use Amires and MASCEM. If you use MASCEM, as you saw in the previous presentation, you also have the results of cross-border congestions, and also you can simulate the intraday market. In the RESTrade, our focus is on the balancing market mechanism, so you can simulate the secondary capacity market and also the secondary energy market and the tertiary energy market. Then on the real time, you can use the real-time dispatch of the optimization models and get the results of the imbalance settlement. So basically, to run RESTrade, we need the input data from the other models. So we need to know the expected demand, a forecast of the demand. We need the results of the day and intraday markets. We need the real-time power balance needs that comes from the dispatch models of the other tools that are provided in the project. So for example, we need to be coupled with MASCEM and Backbone to automatically get these data, or users can select their own data and simulate markets. So why is this important? So in Europe, you have a frequency of 50 Hz, and we have a security margin of 0.1 Hz. So basically, when the supply is higher than the demand and we surpass this 0.1 Hz of margin, the reserves, the control reserves are automatically scheduled to do downward regulation. So basically, the supply can reduce its production, or the demand can increase its consumption to achieve to be in the secure margin. Also, it is mandatory that the security constraints do not surpass 0.5 Hz. And then we can be secure and stable in terms of frequency operation. Now an overview about the balancing markets provided in Europe. So we have the frequency containment reserve, also known as primary reserve control. And these markets can be obligatory and non-remunerated in Europe. And they are not considered in the scope of this system. We have the automatic frequency restoration reserve, also known as the secondary reserve control. And those markets can be remunerated through 4 different schemes in Europe. And the manual frequency restoration reserve, also known as tertiary reserve control. In Europe, different countries consider 7 different schemes to remunerate this reserve in the markets of this reserve. In the RESTrade, we only consider the pay-as-bid and the marginal pricing schemes. These are the most used schemes in Europe and covers almost all power systems in Europe. So how this works: if we have a frequency deviation higher than 0.1 Hz, the primary control is automatically activated in milliseconds, and it can stay active for a maximum of 5 minutes normally. Then to replace this primary control for a new incident in the future, the secondary control is activated normally in 30 seconds to replace the previous one, and it can stay active for 15 minutes. Then in a couple of minutes, the tertiary control can be activated to replace the secondary control for a new incident, and it can stay active for hours depending of the degree of the incidence. The capacity procurement of the automatic frequency restoration reserve, the secondary control, is normally based on the expected maximum demand. So ENTSO-E suggests a symmetrical procurement between upward and downward regulation that considers the maximum expected demand of the power system. So we provide this, and also the Portuguese secondary capacity procurement that considering the ENTSO-E suggestion adds a new parameter that for historical reasons upscales the upregulation between 20 and 60%, because we use more the secondary control to provide upward regulation, and it downscales the downward capacity between 20 and 40%, because it normally has very few users when comparing to the upward regulation. We also provide the option to choose between marginal pricing, and in this case there's an example of the symmetrical ocean clearing. So during a period of time there's a need for up control, in this case 50 megawatts. There are several bids performed for between different players, and the clearing price is the price, in this case 8 euros per megawatt hour, that every player receives for the quantity they bid. You also have the option to select the pay-as-bid scheme. In this case, there's an automatic match of bids. So going to this example, the up control's needs are the same, but only the player that bids the highest value, 8 euros, receive these values. The others receive as bid. So these last players receive 20 euros per megawatt hour when the first one receives 80. So now the new market designs that we are studying. We are studying rolling the gate closures as close as possible to the real-time operation, upgrading them from they had trades for the 24 hours of the next day to trades up to 50 minutes ahead of real-time operation of 1 hour, for example, instead of 24 hours. You also can test right now upgrading from blocks of several hours to 15 minutes product. So instead, as in the other example, instead of bidding for a period of 1 hour or several hours, you can bid for blocks of 4 blocks of 15 minutes or even to 15 minutes blocks in the 15 minutes before. We also consider a shorter product, so to have smaller players participating in this market. So instead of having a minimum bid size of 1 megawatt, we consider also 0.1 megawatts or megawatt hours as a minimum bid size. We also consider upgrading from regulated prices to competitive market-based price. So currently several markets in Europe remunerate these mechanisms using regulated prices. In this case, we also consider the participation of players in markets. We also consider separate procurement between upward and downward capacity and energy. And this is very important because instead of having a symmetrical capacity band, as suggested by NSOE, this can be dynamic considering the needs of the system. And in one period, we can only have, for example, positive capacity because we know that we have lack of energy. In the other period, we can have only negative capacity because we know that we have excess of production, or we can have both positive and negative capacity. So basically, this is the final market design that we allow users to simulate right now in the provided model. So trades up to 50 minutes ahead of real-time operation of 15 minutes products with a minimum of 0.1 megawatts and megawatt hours in liberalized competitive markets instead of regulated prices, considering a separate procurement of both upward and downward capacity. We also provide the traditional market design, so users can both simulate the traditional market designs and these changes to the elements of market designs. We also provide the imbalance settlement, that is the mechanisms that indicates the penalties that the balance responsible parties have to pay for the deviations that they made. And as currently, they only pay for the energy needed to balance their deviations. So in Portugal, we consider a single penalty and a double pricing. So all BRPs pays for their deviations. And we also consider the single pricing Spanish and Nord Pool rule. In this case, we compute the imbalance direction, and only the BRPs that deviate in the imbalance direction pays for the regulated energy. The other ones do not pay penalties. So we can see here the example, while in Portugal, every player that are deviating pays the imbalance pricing. In case the system is in regulation and we have excess of power, using the Spanish and the Nord Pool rule, there's no penalty. Otherwise, they also have to pay the imbalance price if they have a power deficit that is originating this need for up-regulation. So how to run it, install it, and set up the system. So you have to use GitHub. You can install GitHub Desktop, and the upgrades that we are making will be automatically made in your system, or you can download the version that we have, and then we have to download new versions to simulate new upgrades. So because we have the models repository in GitHub, you have to use GitHub. You have to use Spine because it's the system where our models are coupled. To run our model, you just have to install the Java runtime environment or the Java development kit 1.8 or above. It is open access, so there's no cost you can run our system. Here, there's an example of the communication between market models. In this workflow, you have Backbone feeding the project database, and MASCEM and RESTrade both gets data from the database and also adds data to the database. So this workflow is in Spine. The repository with the models is in GitHub. Currently, we provide the coupled version of the MASCEM and RESTrade system. In this link, you can find and download this version or use the GitHub desktop to clone it to your system. So how you can set up the simulation that you want to make. So we have this config file, a row-based file. So basically, if you put in the first row the value 0, you will simulate the new market designs. If you want to simulate traditional markets, we have to put the value that the regulator indicates to the energy price of the secondary energy market. The second row, you may select between a marginal pricing scheme or a pay-as-bid scheme. In the third row, you may select between the NCOE procurement of secondary capacity or the Portuguese one. And in the fourth row, you may select between the Portuguese or the Spanish or Nord Pool Imbalance Settlement. These are the input files and the outputs of the system. So basically, we will provide all these files for our case studies. If you want to simulate your own case studies and power systems, you can go to these files and change these files accordingly to your simulation, to our power system, based on the expected maximum consumption, based on the player bids to each one of these markets. So now I'm going to do a live demonstration to show how easy it is to use the system. So now we have our workflow in Spine. The first 4 blocks is from MASCEM. The last 2 are from RESTrade. This first block is used to simulate the secondary capacity market. This one, the secondary energy market, and the last one, the tertiary energy market and the imbalance settlement. I already made the simulation, so I already ran it. To set up the simulation, all the files are in the root folder of the system, of the repository. So you may go to this file. In this case, I have simulated the traditional markets, considering a price of 100 euros for the energy market, the energy price of the secondary margin. Just putting here as 0, you can simulate the new market designs. So in this case, if you click the first play button, you may run the whole system, including MASCEM and the end market. You can go, for example, to the secondary market or to one of the others, and you can run and see the changes that this market design made to the results. So the results are here in the secondary energy output. So in this case, instead of having a price of 100 euros for the whole periods, the price varies in the periods considering the bids of the agents, both for up and down regulation. So returning to the presentation. If you want to know more about the market mechanisms and the market models we are using, you may see these references. And we also may check the RESTrade user guide and tutorials to know more details about how to use it, and also the market mechanism. So that's all. thank you for attending, and I hope you use this system in the future. And we are here to answer your questions and future emails when using the system for the doubts that you have. So thank you.
Thank you, Hugo. Thank you for the interesting presentation. So is there any question? There is one now in the chat also, also from Tobias Corte. He's asking, what part of the process of integrating the model in Spine did you find most challenging?
The most challenging part is integrating our system with the other systems. Basically, our system is in the end of the workflow, so we need the data from the dual systems. Okay, I can show here the first workflow. We need data from the dual systems. So basically, we need data from those systems. We have to put our results in the database to compute the results of the agents, but the other system doesn't receive data from our system. So the most challenging part is receiving the data and manipulating them from the other partners to be able to be used in our system.
Yeah, thank you. Yeah, I have also a question related to that. What is a spine? Why did you decide to use spine? This is a commercial tool that is also developed by the consortium, or is a different thing?
No, it was developed by another European project, and it is open access. So users, it is free. Users can also, it is present also in GitHub. So users can clone it to their own machine, and then the upgrades are automatic, just like the MASCEM and the RESTrade coupled version. So it provides the workflow between systems. It also has access to the project database using Spine, and users using all these systems are provided in Spine. So currently you are upgrading them, so it's not their final version, it's their demo version, but users can also get these systems and obtain their own workflow. So it is very dynamic. Users can use our own workflows that we provide in the project, but they also can get these systems and use their own workflow as they want. So it is very flexible.
Yeah, okay, thank you. Any other question from the audience? No. Okay, I just have one final question. You mentioned that you provided this new market structure in which you change the gate closure, and you mentioned also like change the mechanism price, the separate procurement, and so on. This market design that you are providing is something that comes from the project, or is something that comes from where exactly?
Yes, it comes from the project. We have a public deliverable 4.5, and we also have another one. So in deliverable 3.5, we have the concept of these market designs. So the theoretical concept of the elements of market design that we should change to be able to have power systems with near 100% renewables. And in deliverable 4.5, we present the models that we are studying. So basically, we have the conceptual deliverable in the deliverable 3.5 when we study several elements of market design, and in the other deliverable 4.5, we put in practice and show the elements of market design that we already implement in this first interaction, and then in the next interactions of these eligible, we will present new market designs.
Okay. Yeah. Okay. Thank you very much, Hugo. And well, we are on time, so we are going to finish this webinar. Thank you, Hugo. Thank you, Gabriel, for the interesting presentation. Also, thank you to all the participants and the audience. Just to let you know that the recordings of this webinar will be available in social media and in the website of the project, which is now in the chat, in case you want to check the presentations. And also there are tutorials of the steps that you need to follow to run these two platforms, and user guides. All of this information is in the website of the project. So thank you again to all. With this, we conclude this webinar, and have a good afternoon to everyone.
Thank you. Bye-bye.
Thank you. Good afternoon.
Thank you. Good afternoon.
Thank you.
Thank you very much. Bye-bye.